Okay, so this is section 2.7, piecewise defined functions. So first, let's think about what is a piecewise function, okay? Now, a piecewise function is essentially just a function made up of different pieces of different functions, okay? It's just piecemeal. We've stuck a whole bunch of different ones together, kind of. So here's some examples. This first one, right, we see that, well, it goes along, it doesn't have, right, a full connection here. It stops right here, and then it jumps up to this little piece over here, and then jumps down to this line section, right? So this one's all broken up in multiple pieces. Then this other one, again, kind of has multiple pieces, but two of them connect right here, right? And then they jump up here and don't connect. So there's multiple ways we can put piecewise functions together. They can connect, they cannot connect, and so on, okay? So that's what they look like graphically. Now, how we write them out as a function is something like this. So if we look here, we see that first it has the function negative x minus 4, but only when x is less than 3, right? Meaning we don't graph it anywhere other than negative infinity to 3 with an open circle at 3, right? So then x squared minus 7 is the next one, but that's 3 to 10 with closed circles at 3 and 10, right? Because it's included, it's or equal to. Then we have 120 over x plus 5, only greater than 10, okay? So it's just pieces of a function located on different sections of the graph, all right? So now let's talk about f of 4. How do we find f of 4 for this function specifically? Now, if we look at this, what we have to think about is where is 4 valid, right? What part of the function does 4 work in, okay? Now, 4 does not work here. 4 is not less than 3, right? That doesn't work. If we look at the bottom one, 4 is not greater than 10. That one doesn't work either. Now, if we look at the middle one, 3 is less than or equal to 4 is less than or equal to 10. That works. So we plug it into the middle one, okay? So that means we have 4 squared minus 7. 4 squared is 16, minus 7 is 9. So that means f of 4 is equal to 9. That is the value of the function when we have this piecewise, okay, at 4. So you have to be very careful on which piece do you use in any case, all right? Now let's talk about domain. When we look at a function, normally domain is just what x's can we plug in, right? We have to be a little bit more careful on this because you have to think about certain things, okay? So the things we have to think about, because it's pieces of a graph, right? Are there any gaps or holes? Well, then you have to think about each piece on its own. What is the domain of each piece? Then what's the entire function's domain when you put all the pieces together, okay? So then thinking about that, really why we think about the domain for piecewise is if we can use all of our x's. Like before, maybe 4 wouldn't have worked. If 4 didn't fit in any of those 3 different kind of domains, right? Then, well, 4 wouldn't have been a valid point to plug in. We couldn't have plugged it in. It would have been empty, right? The empty set or the not kind of valid number, okay? So, after that is kind of talking about what the pieces of a function are called when we set it up as a piecewise. So the function name is the first thing there. P of t is this function. Then the function pieces, kind of the other functions that we use to make it up. And then the domain of each piece is given with those inequalities, okay? So that's kind of all the different sections of how we write a piecewise out. Now, the next thing, how do we graph one of these? Okay, when we look at this, well, we have to think about where we graph them, all right? Now, it's important to notice, again, right, this one's only 0 to 3. That means this graph, if we think about it on a number line, we have 0 to 3 with full filled in circles for that first one, right? It's good enough for me. So it does something in here, right? We're just thinking on a number line, just X values that we plug in. Then the next one, let's put that one in red. This portion, that is 3 then to 7, but its 3 is not filled in because it's not or equal to. 7 is, however, so that one is just from 3 to 7. So they overlap. The domain of the entire function would be 0 to 7 because 3 is valid in at least one of them, okay? So that's kind of how you have to think about it first, is where do we even graph these, right? The next thing we want to think about is kind of, let's write out a chart almost of values, of points to plug in, okay? So we have X and Y. Now, the thing you want to do is you definitely want to plot the end points of each section. Meaning, even if it's an empty circle, even if it's technically not valid to plug it in, right? You still want to know where it would have been, kind of thing. And you just put an empty circle maybe on it, okay? So, first, let's do the top piece, right? The negative 2x plus 10. So if we plug in 0 there, well, negative 2 times 0 is 0, plus 10 is 10. So there's our first point. We can plug that in with a filled in circle. If you want to note that, then that's fine. Filled in circle. Then let's do a point in between. So in between 0 and 3, let's do an easy one. Let's do 1, right? So 1, if we plug that in, negative 2 times 1 is negative 2, plus 10 is negative 8. That is still a filled in kind of point, right? Not an empty circle. So then, let's go ahead and then do the other endpoint of 3. If we plug 3 in, negative 2 times 3 is negative 6, plus 10 is positive 4, right? Wait, hold on. Why is this one negative 8? It should have just been 8. Sorry about that. So we'll take that negative off. I was wondering why that didn't make sense. So we have this 3, plug in, get 4. Because we still have less than or equal to 3 for that top piece, it is still a filled in circle, a full point, okay? So now let's look at our second piece. Even though it's an empty circle at 3, it still kind of starts there. So we still want to think about plugging 3 into it. So that one's a little harder. We have 3 squared. The negative is not inside the square, so be careful on that. 3 squared is 9, so that's negative 9 plus 3 times 9 is 27 minus 14. Negative 9 plus 27 would be 18 minus 14 is 4. Okay, so note for sure this is an empty circle. Okay, now let's get another kind of middle point. So let's something in between 3 and 7. Let's do another easy one, 4. So 4 squared is 16, so negative 16 plus 36 minus 14. So negative 16 plus 36 is 20, minus 14 is 6. So that, because it's an actual point, will be filled in. Okay, now let's go ahead and do our endpoint of 7. 7 squared is 49, so negative 49. 9 times 7. Now, I know we can use a calculator in this class, but I have a really cool trick that I want to show you for multiplying by 9s, at least up until 10. So, because we're base 10, we have 10 fingers, right? If we want to multiply by 7, you put down your 7th finger. So I'll turn to the camera so it's in the same direction. So 1, 2, 3, 4, 5, 6, 7, 7th finger down. Multiplying by 9 then is 63, because you have 6 fingers on that side of the bent down number and 3 numbers on that side. So that's my little trick, because I didn't bring my calculator with me. So we have plus 63 minus 14. So negative 49 plus 63 is 14, minus 14 is 0. So that is an or equal to, so that is a filled in point again. All right, now we plot those points on our actual graph now. So our first point is 0, 10. Now unfortunately the graph that I put on here doesn't go up to 10, but we'll just make do by just kind of putting it up here-ish. Okay, it's a filled in circle. Alex will never do this to you. It will always give you the graph, the full graph that you need. The next one is 1, 8. So 1, again, a little bit above, about there. Then the next one is 3, 4. So 3 goes up to 4 and is a filled in circle. So this is just a line, right? So it should be straight. So we go here to here. Okay, more or less. It's not perfect, but Alex will kind of perfectly graph it for you. Okay, now the next ones. We have 3, 4 with an empty circle. Well, we already have it there. If you want, you can just kind of put an empty circle around it. That's fine. It doesn't matter to me. It won't matter to Alex. Actually, I'm not sure if it will matter to Alex. Don't put an empty circle over a filled-in circle in Alex. I think it will overwrite it, and you definitely want it to be a filled-in circle because at least a point is there from the first piece, if not the second piece. Okay? So, it's a point there at 3, 4. Then 4, 6. So 4 goes up to 6 right here. And then 7 goes to 0. So at 7, we're at 0. This portion of the graph, its parent function is a squared, right? So it has the behavior of looking kind of like this, more or less. Okay, again, Alex will graph it a little bit better looking than I did, a little bit smoother, okay? But that's our parent function. Now notice I put an arrow there. I shouldn't have, right? Because it stops there. So I'm going to erase that part of it and just join it right here because it stops at 7, so I shouldn't have put an arrow. If it just went on for infinity, just 3 is less than x, well, then we go on forever after 7 even, okay? But that's more or less how we graph a piecewise function. You have to look at each piece and find points, plug them in, okay? Not too bad. It's just really, it's kind of like graphing multiple graphs just on one Cartesian plane. Now, the next thing we want to think about is continuity. So first, let's think about the word itself. What does continuity mean? Okay, so the dictionary says it's marked by uninterrupted extension in space, time, or sequence. That means almost absolutely nothing to us in this context. So let's think about it in math terms. So basically, continuity means no gaps, no holes, no breaks in the graph. If you can draw the graph without picking up your pencil, it's continuous. And another way of thinking about it is every x between the beginning and end of the domain can be plugged in. So essentially, going back to that previous example, right? If we look at this one, everywhere in between 0, right, and 7, we can plug all of those numbers in, right? So that's kind of a good way of thinking that it could possibly be continuous. Now, the next thing you have to think about is, do the pieces connect? That's also something you have to think about, okay? So it's not necessarily just can every x between the beginning and end of the domain be plugged in, but do the pieces, right, because it's a piecewise function, do they connect in the middle or are they separated, okay? Now, You can have piecewise functions be continuous or discontinuous, okay? They can be either. It's not better or worse to be one or the other. It doesn't make it right or wrong, okay? It's just continuous or not continuous. So continuous, like we said, no gaps in the domain of the pieces, okay? And the pieces connect. Discontinuous, well, gaps in the graph and the pieces don't connect. It's pretty obvious, right? It's either it doesn't have gaps or it does. So now some visual examples. This one, the one on the left, the continuous graph, notice the pieces, because it changes kind of behavior for this section over here, right? This point right here is the point that you have to check. Do the graphs or do the pieces connect? On this one, yes, they do. So this graph is continuous. If we notice here, this gap right here, right, that's the issue. They don't connect there, so this function is discontinuous, okay? So that's what they kind of visually look like. It's hard to tell just by looking at the function notation itself of a piecewise if it's continuous or discontinuous. It's much easier to look at a graph because visually, right, continuity is very obvious, okay? So let's do another example in Alex of actually graphing out a piecewise function this time. So now I've left kind of the screen open here so that we can write out, because I cannot write on the internet screen portion. So first, well, let's think about number line. We go, well, this one is just when x doesn't equal -3, right? So everywhere it doesn't equal -3, -2, -5, 0, infinity, -infinity, all of those places, we use that function. So number line, we think, right, we have just -infinity to infinity. We just care about -3. On that portion, that first piece, we have an empty circle there. We do not use -3, okay? Then on the second portion, we do use -3. Okay, that's the only point even that we use, because notice, right, it is only -3 if x is equal to -3. Okay, we've basically kind of pulled out a point from the first piece and just plopped another one in. Okay, so let's see what that looks like. Let's plug in 2 into the first graph on each side of -3. Okay, so if we plug those in, let's see what that looks like. Let's write out our chart again. So we have x and y, and then we say, let's see, negative, it really doesn't matter. You can plug in whatever you want. Let's make sure that it will fit on the graph that we have. We only go out to -5, so let's not go further than -5, right? So we don't want to do -3, so let's pick -5 and -4. Okay, so what's the graph again? X over 2. So we have x over 2, and we want to plug in -5. So -5 over 2, well, that's just -5 over 2, or if we wanted to write it in decimal form, because we can plot those out to the half mark on the graph that they gave us. So -5 divided by 2 would be -2.5. Let's also plug in -4. -4 divided by 2 is -2. Now remember, skip -3 because we have that open circle for that first graph. So let's go to 0, right? If we plug 0 in, 0 over 2 is 0. That's a nice point. Then let's do 2. If we plug 2 in over 2, well, 2 gives us 1. We just basically didn't want to plug in -3. Just skip that one over. So now let's go over to the graph and plot those points. So which option here do we want to choose? Well, okay, what we want to think about doing here is, do they go in both the directions, or do they stop? Do they have endpoints kind of thing, right? What's the end behavior? That's what we should think about. So really, let's think about this again. Well, we actually do want to know what -3 would have looked like because we want to put an open circle there. So even though it's not truly in the function, we're not using it, we still want to know where it would have been because we have to connect to it. Because -3.00000 infinity 1, right, is valid in x over 2. Also, -2.99999999999 forever, right, is also valid. So we want to get up to close to -3 as far as possible. That means just putting an open circle wherever -3 would have been. So let's actually do -3. -3 over 2, well, -3 over 2 would be -1.5. So we should put an open circle there. So let's choose the open circle. At -3, we go down 1.5. So open circle there. Okay, now, well, let's think here. How do we connect to this then? Okay, so we can connect by choosing kind of this line right here because it starts and then goes forever in one direction. We don't want this first line option because it's a line that goes forever, right? We don't want that one. This one has a start and a stop. We have a start but not a stop, okay? So you want to choose this third option. Third option is grabbing it here, right? And then, well, let's see what it looks like then. First, well, we have -5 to -2. So, well, actually we want the closest one. We want -4 to -2. So -4 is at -2. Then let's make sure it works. -5 was at -2.5. That's correct. Okay, so let's plug in then the other side, right? We choose this option and we again place it at the empty circle. Then 2 goes to 1. Well, that's one of the options. We could also do 0, 0. Let's do 0, 0. 0, 0. Then 2 goes to 1. Also works. So all of these first points are good. We did our empty circle at -3, -1.5. We now just don't forget to take care of that second piece. The second piece, again, is only valid at -3. So we pick the full circle here. If we plug in x is -3, we get -3. Even though there's no x, that just means, well, that's the line at -3. It's a horizontal line. Any x we could have possibly plugged into the parent function of that one would have given us -3. So we plug in -3, we get out -3. That is our function here, okay? Now if we look at this, is this function continuous or not continuous? We should kind of think about that. So it is not continuous because, sorry, hold on, let me choose a different option here. This point right here is separate. If we want to draw this line, I would draw along here, open circle, and then I have to skip down here, right? I'd have to pick up my pen or pencil, meaning there's a gap, right? A hole in the function right here at -3. If this point, the second piece, had filled in that hole, right, made it all connected, well, then it would be a continuous function. However, because they're disconnected, right, it's two separate pieces, this is not a continuous function. Okay, so that is lesson 2.7.